Welcome back to Polybridge. I hope to get several more levels done this time. I also have some interesting observations queued up in my little notepad file here, but we'll get to those in due course. Let's get into building some bridges. So I think last time we did first drawbridge? No. Checkpoints, yes. Okay, so we're on first drawbridge. This says use hydraulics to create a drawbridge, so they're going to teach us about hydraulics and using hydraulics. And you can see from this little thing here, the sort of order of operations. First, some hydraulics are going to move. Then the little hydrofoil boat down here is going to come through. Then some hydraulics are going to move. We get to choose which hydraulics. And then the little scooter is going to go across. So from the looks of the support points, you can see we have support points down here. I guess the really obvious thing would be to sort of build a bridge. Let's see, I'm doing 9. Arc tool. Actually, we're not going to use an arc, we're going to use a line. And then we'll just fill this in with regular road, which we have selected down here. Let me just make sure. I'm hitting 1 to go back and forth between the roads as usual, and then 0 to just fill it in. So, from the looks of this, the really obvious thing would be this section of road right here, and that section of road right there would get pulled upwards and out of the way by hydraulics, presumably, since hydraulics is really the only means we have to move things around. And so I think we'll just do it that way, just because. I guess, just for the sake of amusement, I will truss it up. So let's make sure, I think I hit R to bring the auto-triangulation on. We want 4 meters at 60 degrees. Okay. And we want this to be as level as possible. So what I'm going to do is hold down the W key to just erase individual things. See how the eraser appears? And now we can copy this and just paste this all the way across. And then again, W just allows us to delete just this one. And I'm just going to run the simulation really fast here just to make sure this can support its own weight. I strongly suspect it will, but just for my own amusement. Yeah, so, you know, things turn orange, but the bridge supports its own weight. This little scooter only weighs 1.5 polygrams, so it weighs almost nothing, trivial compared to the weight of the road. So, if we're going to pull upwards on this point, then clearly 2 things are going to have to happen. One is, this is going to have to go. Right? And I guess, I don't know if these can be replaced with hydraulics or not, but it's worth a try. So we'll pop these out. And again, this is a symmetrical bridge design, so how about we just design half the bridge? The supports down bottom look completely symmetrical, so I think we can actually just nuke that. Okay, so this guy doesn't actually have to go up very much. Let me turn on the grid with G. Got scope 1, 2, 3. I guess we should bring this up a full meter, and that would be up to this intersection of the 2 solid lines right here. Well, probably when it swings up, it's going to move over here somewhere, but okay. And then do we have a full meter here? Yeah, we have, looks like, almost 2 meters, so, I think the sneaky designers of this level were intentionally designing this to make our life easy. And the reason I say that is, hydraulics, generally speaking, when they contract, they can only contract to 50% of their maximum length. And so if we have 2 meters to contract, that should, in theory, bring this up just about a full meter. Anyway, let's do that with a hydraulic. And contract 50%, yep. And I can't contract more than 50%, right? Yeah, okay. And let's just copy all this and just flip and paste it. So right-click, C to copy, F to flip it over. And because we don't have a compressive element here anymore, pulling downward on this node will just bring these 2 nodes closer together. So I think we're going to need supports from underneath. We have steel and we have a $25,000 budget, of which we've only used about $13,500. I think I'm just going to be super cheap and cheeky here. And honestly, that looks pretty good. We actually, so this node, we don't want it to be supported because that's going to have to come apart. So let's do something like, yeah, that looks good actually. Okay. That cost us about $2,000, but I mean, we had like $12,000 to work with, so copy and flip. And again, just for a giggle, I just want to see if this supports its own weight. For the moment, let's just hit space and see what happens. Ah, okay. So, because these are sloping inward, there's a tensile force pulling this way. And so I think we're going to actually need to... and it won't actually let us do that. All right, so we'll go ahead and just, triangulate this up and trust that the tension forces will come down through here. I am going to... Oh, sorry, grid's on. What I want to do here is I want this steel to be as close to straight as possible so that the tension forces travel through that relatively straight. Okay. Now, I think there should be no issues at all. Whoa, okay. So, I don't know if you saw what happened there and the reason why it happened. Let me just delete these two, and then we'll run it again, and you can see... See how there's no problem here? So, what happened was, the hydraulics started going, and as the hydraulics pulled these two nodes together, that actually broke these guys down here. So I think that's a pretty good confirmation that our structure is supporting this bridge, no issues at all. Hang on a second, my OCD. I'm going to use left shift and pull this down until this is more or less straight. This just looks really weird with this bizarre thing in the middle, but whatever. I'm not going to worry about it. I'm not sure if that should go the other way, but since steel is just as strong in tension as it is in compression, honestly, I don't think it really matters which way that goes. Oops, sorry, let's do this first. Delete. Copy, flip. Okay. Now, remember what it said back at the... So it said that first there was going to be some hydraulic movement, then the boat was going to come through, then there was going to be some hydraulic movement, and then... So, there's a thing you could do called making a joint, and a joint is a node in the bridge that will split apart. The way that you make a joint is you hover the mouse over a node and you type the J key. Now, this gets complicated. Suffice it to say, when this node comes apart, and you can choose when the node comes apart and when the hydraulics move, when the node comes apart, things with the same number stay together, things with different numbers split apart. So in this case, these two members will stay attached to the yellow side of the node. And these two, because these are number 2, they will stay attached over here. Now if we did something like this, then basically everything would come apart and the whole bridge would just fall apart. Why don't I just show you? Right? So clearly that's not the way to go. We want these two parts to stay together and to stay attached to that node. Likewise, we want these two beams to stay together and stay attached to that node. However, we want these two sides to separate from each other. Now let's make sure this works. And is that enough? It's just enough. We knew it would be. And now when these come back down, they should lock back together and you'll see a yellow flash. There you go. So I am a tiny bit over budget, and I'm going to see if I can replace some of this steel down here with wood, because some of these might have to be this long, but others might not. So let's just experiment over here. And I guess because this supports this end of this one very well, we don't actually need to do anything there. We really only need to support these 3 nodes. So let's just build, what, like -60. Again, I want these to be like equilateral triangles if at all possible. Just because I love Warren Truss. Okay. And then try and make this as level as possible. Good. And then... I don't know. I am pretty sure that this is not going to be strong enough to support all this. So maybe we'll have to make this one out of steel. Anyway, let's run simulation and see what happens. That's already going orange, which is not a great sign. Yellow locked together. Wow. Okay. So, I did not expect that, but okay, fine. And we could delete some of these truss members up here because this node in particular is supported from the bottom, so it doesn't really need truss on top. We need these two triangles because they're the thing that hooks up to the hydraulic, but like this stuff here, we don't need all of this. So let's go ahead and delete this and put a copy of this over here. Copy and flip. And we're way under budget, and so although... What the hell? Just to make me feel better, let's steal this and this. Now this is incredibly strong. There's not going to be any chance of any problems with that. And we're still plenty under budget. So let's test this. I guess I'm not going to show you hydraulic controllers yet. They don't introduce us to that mechanic just yet. For the moment, I think they're just trying to explain to you about split joints. So yeah, let's just do this. And very low stresses. So the bridge is overbuilt, which is good. I like overbuilt bridges. Overbuilt and under budget is good engineering. So let's see what the maximum stress was. Maximum stress was 22%. One more thing here before we move on. See up here you can see stress visibility. That's what causes the parts of the bridge to change color when the stress goes on them. Now that I know that the maximum stress is like 20%, I want to be able to see the normal colors of the things on the bridge instead of the stress. So I'm going to turn stress off, and then I'm just going to run the simulation. There you go. Now we can see red steel, we can see the blue of the hydraulics, we can see the tan of the wood. Glorious. So we have a safety factor of just under 5, and we're under budget. I'm loving it. That's fantastic. Let's move along. So what they're doing now is they're forcing us to build a bridge where not only can the car go up the bridge, but it can also turn around and go back down the bridge. I don't anticipate much in the way of challenge here. This is really a lot like that level where we had a bridge on a slope. And then we just have to add one more piece here. My guess is, even though this is not quite perfect, I'm just going to move this up. This guy just a little bit. This guy down just a little. A little bit of a hybrid between a Warren and a bowstring truss. My guess is this going to have no issues at all holding its own weight or the weight of the taxi. So let's just run the simulation, just see what happens. Gotta tell you, the stress has got a lot higher than I ever expected. Maximum stress 97%. So let me see. We're so low on budget. We're like under half our budget. So let me just fiddle briefly with some of these. And if I have to speed this up in editing just to lower the stress just a little bit. That looked like it topped out around 91. 92.7. So yeah, sure. You could totally, if you wanted to, you could absolutely use steel anywhere along here. You could use reinforced road. I'm perfectly fine with this. Let's go ahead and move along. Let's go on to the next one. Rope supports. I have some interesting stuff to say about this one. Rope and cable are strong and long, but they cannot be compressed. In other words, they have no strength and compression whatsoever. So you have a long span. Let's measure the span with the line tool here. 25.94 meters. Might as well be 26 meters. And we have a relatively heavy 10 polygram fire truck. But now we have ability to have tension, cables, or ropes. And I think I have some like saved and loaded solutions. So let's hit escape. No, I think it's here. Load. So this is how I did it. I used ropes to support some nodes in the middle, just under pure tension. And then I used really, really small trusses, really small bowstring Warren truss to support the pieces of road in between where the ropes hung down from. You can see I crossed the ropes over here. I think I also had something to say about using ropes in ropes in Howe truss. Let me hit my little 1/8 rope support. Ropes in the game have shockingly little stretch. I expected tensile forces on my roads due to rope stretch. Nope. Also, why is rope so frickin' expensive? The verticals in a Howe truss are in tension, so they could be rope if rope was economical, and I think that was the one thing that I wanted to say is, rope is $220 per meter versus wood at $180 per meter. Tell me how that makes sense. I mean, I understand cable is made of steel, very good, high-quality steel, and you have to braid it up or wind it up, so I understand why steel cable is expensive, but rope being $220 per meter and wood only $180 per meter? Yeah, I don't believe it. I guess the only other thing we're saying about here is, you see these little braces underneath here where if something pushes down on this, it compresses that, and then the compression is forced to push into the ground because this guy goes under tension. This node can't fall downward because it's being held by this little link, so any compressive forces get pushed right into the wall. We got stress on. Yeah, let's see what this does. Wow. That's a lot of stress. But you know, I don't actually think most of the stress was on the ropes. I think actually most of the stress was on... Let's run this again half speed. I think most of the stress was actually on these tiny little trusses, which frankly don't need to be so goddamn small. I think I was trying to get under budget, and I intentionally made trusses that were really small, but they didn't need to be that small. I have almost $4,000 to spare here. I think it's these guys turning red. That one turns really red. That one turns pretty orange. Those turn pretty orange. This actually gets a little bit stressed. Little orange here, red there. So yeah. Alright, fair enough. Let's move along to the next one. Ah, yes, budget cuts. This is another one where I think I had something to say about it, because the title of the level, in my opinion, is a little bit misleading. And we're going to use an RCE, a real civil engineer technique called a muscle here, which I'll show you in a minute. This says use less material to save budget. So I think they're trying to tell you to use the minimum amount of material, but for starters, I believe that you cannot do this with regular road. I think you have to use reinforced road at $400 per meter. So, like, yeah, you use the same number of chunks, but they're twice as expensive per chunk. Meh. And then they don't even give you steel, which, you know, this kind of looks like a steel bowstring truss with maybe a little support down at the bottom. So let's go ahead and load what I made, and then I'll talk a little bit more about it. Yep, use muscles. So, see this thing right here? This weird little double diamond shaped thing? This is something that Real Civil Engineer taught me about. He called it a muscle. I just call it a double member, or basically, if you have a force pushing down or pulling on this node right here, about half of it will go down each of the paths. And so this essentially allows you to have this particular, instead of having a single piece of wood here with whatever strength it has, you have at least double, maybe a little bit more than double the strength. Other thing to note is that I've clearly had to use a reinforced road right there, not a regular road. So there must be some kind of either heavy compressive or heavy tension stress on this little bit right here in order to force me to use reinforced road and a muscle or doubled member right there. Also, I really like so you notice that over here I didn't need any of the fancy stuff because apparently this little segment of road here allowed me to build a stronger supporting structure out of wood underneath, and it was strong enough to handle, what is this, 11 polygrams? Yeah, he's pretty slow and he's pretty heavy. Over here though, I had to use a long section of road, reinforced road, and a muscle or a double member to support it all. Other than that, very nice symmetry. It's also interesting to notice the size difference between these. This guy is taller than this one. So again, clearly we're having things where slightly different side to side. Let's run this just so you can see it doesn't break, and then I'll try and copy this half of the bridge over to here and see if it'll support it. But first let's run it so you can see. A lot of load here. Going orange for sure. And then a lot of load on these, going up to 82%. A lot of load on these, going up to 83%. A lot of load on these, going up to 87%. So let's see how that actually stacked up. Maximum stress 95, so yeah, very interesting indeed. So let's just nuke this whole half of the bridge. Remember, I have this bridge design saved, so I can pull it back anytime. And then we'll copy this, and then use F to flip it. And just for a giggle, actually, I'm going to even... Well, let's see if this works at all. And if it does work, then great, nothing more that we need to do. If it doesn't work, then I'm going to go ahead and use left shift to sort of pull these up and make these bigger, although truthfully, it isn't these members up here that are getting overstressed, it's this stuff down here and these guys. So let's see how this goes. I'm curious. Oh yeah, oh it's gone. Yep. So I'm curious to see what the little red box will tell us actually broke first. That. So you can see how this design evolved. I probably started with a symmetrical bridge like this, and then found out that I couldn't actually make this strong enough, and so I ended up changing this to reinforced road and using a muscle, and that is how I got this. Very interesting indeed. Okay. Let's see if I had anything else to say about this. Yeah, use minimal material. Actually, you need a muscle. In order to make this work, you have to use a doubled up structural member here to support the load. And number 10, first jump. Okay. Sometimes jumping the gap is the best solution, and I think the other thing that they didn't tell you is this is your introduction to springs, where instead of rigid members that if they take too much stress, they'll just break, you can use springs, which have some give. The other thing to notice here is that they've only given you 8 pieces of road to work with. So there's no way, if we take out the curve tracer tool here and try and go down here, and we'll fill this with road. Like, I don't even think this is going to get even 1/3 of the way with road. Yeah. Basically, it gets halfway there, and then you're done. So, yeah, that's not going to work. So I'll show you what I did. I just essentially made a little curvy ramp here, and then I made a little thing down here that is supported by a bunch of springs so that when all the weight and the inertia of that car coming down here hits the road, the springs take up all the force. First of all, allow this not to break, but second of all, allow the car to successfully get to the flag. So let's load this up. Springs to absorb shock. So you can see I used a lot of steel. So there's that guy. Reinforced road. And down here, essentially just constructed a steel thing with a soft landing ramp. And I didn't pre-stress. You can pre-stress the springs just by dragging them. So you can stretch them out or you can compress them, and that way they'll shrink or expand when you hit spacebar to start the level. But I didn't find I needed that. I just needed to make something that would just take the weight of the car. Let's watch how this goes. Zoom out just a little bit more so we can see everything. All right, you ready? We're going to watch in half speed for more drama. Nice. And the maximum stress was only 81%. Even though that landing looked really rough when that car came down to hit that. Not bad at all. The springs really did a great job of absorbing all the energy and allowing the car to get on through. Love it. Ah, yeah. Now this one, stop and go. Some checkpoints will stop the car. I believe I had something to say about this, like basically, there's no actual need to stop. You just build an arch. Let me just show you. Oh. You can just build a shallow arch right over top of this. You don't need to stop. I think I actually saved this so I can show you guys what that looks like. Instead, though, because you do have to stop, what we'll have to do is we'll have to sort of build a bridge out to about, I don't know, let me just start building here. I think that's fine, and then we'll do the actual arc up and over. The arc has to be kind of gentle because there's not much ground clearance beneath this VW bus, and his bumpers tend to hit the road if you're not careful. I think... Oops. Didn't need that, so we're going to use W to erase that. Put it back as regular bridge. There we go. And then we'll truss over top of this part. With wood, of course. I hit 2 to get wood. Just trying to make that level. Looks good. Oh, wow, okay. Interesting. There we go. So, you see how when I move this up, that node turns a little darker. When I move it down, it turns a little lighter. So just for my own amusement, I'm just going to let the cars run and make sure that at least the little car will get over there no problem. Yeah, there's no issues at all. No stress happening. All right. Let's go ahead and use an arc. So we're hitting 9 to get the arc tool. And we're going to do this in regular road, actually. And then we'll go over there. And then we'll see how much we can cheat this down. Remember that the road has some thickness, so you can't get super close. You have to deal with the thickness of the road. And again, I don't want to make this too sharp an angle. Like, doing that would be bad, because the bumper height of this thing will just smash right there if you're not careful. So let's kind of try to do a curvier bridge with a little bit more of a bump in the middle, because we can afford to. That seems pretty good right there. And then we'll hit 1 to select normal road, and 0 to just fill it in. You know, that is a little sloppy, but I think it is going to make it. I'm going to go ahead and take the risk and say that this probably does make it. Again, we're just going to truss right up and over this. To make sure I've got auto triangulation on, I do. I think that's going to work just fine. Let's just see if the boat hits it. Only thing I'm worried about here is the boat hitting this on the way through. I'm pretty sure this guy's bumper is going to clear that no problem. And I'm sure that the car is going to get over that. So the car just goes right over. The van chooses to stop right there. Fine by me. You can see this guy's wheel is a little bit off. So I may have to dicker with this just a little bit to make that slope less steep. The boat clears. Let's see if the van can... Alright, well, in theory, if I sat here long enough, he might be able to climb his way up, but it's really, really easy just to hold left shift and just pull this all down a little bit. Make this just a little bit less steep. It's rolling backwards a little bit. Oh, it's still too steep. It's really annoying how shitty the ground clearance of this dumb van is. But he makes it eventually. And since I am so under budget, and looks like the maximum stress was like 40-some%. We'll tweak this just a little bit more. Almost straight, but not quite. There's a hashtag your dad joke in there, but I won't make it. I think we've pretty much gotten this as good as it's going to get, but what we could do is... And that way, the change in slope here, the angle, is even more gentle. And even the really shitty ground clearance of this VW bus shouldn't be an issue. No issues at all now. Wheels stay firmly on the bridge the entire time. Yep. I'm more than fine with that. I think maybe it's time to end the recording session. However, let me just look at my little text file here. Okay, I think I saved this one so we can squeeze in 112. 114 for sure we're not going to be able to do because it's actually a much longer level and much trickier than it looked. Let's just do 112 real fast and then we'll end the video. Perhaps we can use that rock to our advantage. The thing that I wanted to say about this is even though there isn't a red anchor point here, you can build a little structure on top of this and let gravity do most of your work. That wasn't the most surprising thing to me about this level. The most surprising thing to me about this level was, after building my little gravity support thing in the center here, I just made 2 long sections of bridge, each of which just had the Warren truss above them, and it just worked the first time. Let's see if I saved this. No, I didn't. Okay. Maybe I'll have to fast forward you through this. Anyway, let's get out the trace tool. We're going to do a straight line from here to here, in regular road. Fill it in. All right. And we'll throw some wooden supports underneath. It's just right here. I think I did something approximately like that. And then the rest of this is just bog standard Warren truss. Be there in a minute. Okay, place your bets. Do you think this is just going to work the first time? Or is it going to break and die because of too much stress? My expectation the first time I ran this was, this is absolutely going to break and die because of too much stress. Let me... Just want to like make sure these are firmly on the ground. All right, let's see what happens. It did fall a little bit in the middle, but that's okay. That just means that those nodes are now very firmly in contact. Getting pretty orange up here. Wow. What was max stress? 71%? Just for like a super brain dead little underneath support with a couple triangles and just dead simple Warren truss up at the top. Wow. I did not expect that to just work the first time. That's it. We're going to stop the episode right there. I think I have more than enough footage to make another episode. Hope you've enjoyed that one. Hope you learned something about building poly bridges in the Polybridge video game. And hope that you're staying salty, my friends.